On March 24, 1941, the engineers at George A.T. Fuller Company in Rhode Island gathered around a conference table covered with blueprints. They faced a challenge that seemed almost impossible. The United States Navy had set them a task that would require miracles in mathematics and manufacturing. They needed a portable building that untrained soldiers could put together in enemy territory using nothing but hand tools. It had to be stronger, faster, and better than anything the British had built in the First World War, and they had less than 60 days to make it happen. Across the Atlantic, the British had been using the Nissan Hut for a quarter century. 6 men with 4 hours of time could assemble one on prepared concrete. Under perfect conditions, with a specialized Royal Engineers team, the record stood at 1 hour and 27 minutes. But the American military wanted something that didn't just match this performance, they wanted to shatter it. They wanted speed that would transform how warfare itself was conducted. What the British and Germans failed to grasp in 1941 was that American thinking about construction was fundamentally different. The coming American design would not be an incremental improvement measured in inches or slight weight savings. It would represent a complete philosophical shift. Speed of assembly mattered more than established tradition. Simplification beat complexity. Any soldier carrying a hammer needed to build shelter as easily as he could fire his weapon. The contrast between what America was about to accomplish and what Britain had achieved reveals something deeper than just engineering skill. It shows two entirely different industrial philosophies at work, two competing approaches to warfare, and two opposite visions of what prefabricated building could become. This is where the Quonset hut enters history. To understand this revolutionary structure that could be assembled in hours rather than days, one must go back to 1916 and the birth of its predecessor. Major Peter Norman Nissen of the Royal Engineers began experimenting with semicircular shelter designs as the Battle of the Somme loomed ahead. The Western Front needed housing for hundreds of thousands of newly conscripted soldiers, and conventional building methods simply could not keep pace with demand. Nissen, a Canadian mining engineer and inventor by training, found his inspiration in an unlikely place. A drill shed roof at Queen's University in Kingston, Ontario, featured a semi-cylindrical design that had collapsed back in 1896. Rather than seeing failure, Nissen saw possibility. He recognized that a semicircular structure would deflect shrapnel and explosive blast better than rectangular buildings with their vulnerable right-angle corners. In just 3 days, between April 16 and 18 of 1916, Nissen constructed and tested 3 prototype huts. Officers including Lieutenant Colonel Shelley and General Clive Gerard Liddell reviewed his work intensively. When the 3rd prototype proved successful, the design received formal approval in August 1916. The beauty of the Nissen hut lay in its elegant simplicity. Curved corrugated steel sheets formed the outer skin, attached to T-shaped steel ribs spaced 6 feet apart. These ribs bolted to floor bearers at each end. Wooden crosspieces ran lengthwise between the ribs, giving attachment points for the corrugated panels. 3 standard widths were available, 16, 24, and 30 feet, with lengths coming in multiples of 6 feet. The most common size measured 16 feet wide by 36 feet long. The exterior used corrugated steel sheets measuring 10 feet 6 inches by 2 feet 2 inches, overlapping by 6 inches at the ends and 2 corrugations at the sides. About 54 sheets would cover a typical 16-foot hut. The interior could be lined with additional corrugated panels or pressed wood, creating an airspace for insulation. Wooden frames with doors and windows capped each end. Assembly required 6 men, a prepared concrete base, and roughly 4 hours of normal work. The crew would bolt the steel ribs to the foundation, attach the wooden crosspieces to the ribs using hook bolts, then nail the corrugated sheets to the wooden pieces. During assembly, straining wires on each side of every rib needed tensioning to prevent the structure from spreading outward. The entire structure could be packed into a standard 3-ton army wagon for moving. By the time World War I ended, at least 100,000 Nissan huts had been manufactured. Major Nissen received promotion to lieutenant colonel, earned the Distinguished Service Order, and obtained patents in the United Kingdom, United States, Canada, South Africa, and Australia. Remarkably, he waived all royalty rights for the war's duration, and Nissan Buildings Limited did the same again during the Second World War. Yet soldiers living in these huts rarely loved them. In the United Kingdom, men found them cold and drafty. Those stationed in the Middle East, Asia, and the Pacific found them stuffy and oppressively humid. The airspace insulation provided only minimal protection from temperature extremes. Early versions had dirt floors, no electricity, and only potbelly stoves for warmth. But despite these discomforts, they were portable, reusable, and far superior to canvas tents in combat zones. Production slowed after the First World War, but picked up again in 1939. Other designs appeared, including the Romney hut in Britain and eventually the Quonset hut in America. The Nissan remained the standard until American engineers asked themselves a question that would change everything. What if they eliminated the internal framework entirely? In March 1941, the George A. Fuller Company of New York received an urgent request from Admiral Ben Moriel, who directed the Bureau of Yards and Docks. The Navy needed thousands of prefabricated structures for bases being constructed along the Atlantic coast and throughout the Pacific. These buildings had to be light enough to ship anywhere in the world, strong enough to survive hurricanes and typhoons, and simple enough that untrained people could assemble them using only basic hand tools. The Fuller Company was already building facilities at Quonset Point Naval Air Station in Rhode Island. This firm was among America's largest construction contractors. They had constructed the Flatiron Building in New York and the Lincoln Memorial in Washington. Now their design team, led by architect Otto Brandenberger, along with engineers Robert McDonald and others, received what appeared to be an impossible mission. Create a revolutionary prefabricated shelter, construct a factory to make it, and deliver the first units, all within 60 days. The Navy provided Fuller's team with British Nissan hut plans as a reference point. Brandenberger and his colleagues studied the design carefully, recognizing its strengths and seeing its limitations clearly. The semicircular shape was structurally sound and aerodynamic. The corrugated steel was weatherproof and relatively light. But the Nissan hut's internal framework of steel ribs with bolted connections created assembly complexity that slowed everything down. The Fuller team made a decision that would prove revolutionary. They would keep the semicircular shape but completely reimagine how the structure would hold together. Their approach would move complexity from the job site to the factory, dramatically reducing assembly time in the field. The Fuller Company constructed a sprawling manufacturing facility near Davisville, Rhode Island, in just 30 days. So confident were they in their approach that production actually began before the engineering team finished all the details. This aggressive strategy would become typical of American wartime industrial thinking. Get it in production now, perfect it later. The original design, called the T-rib model, measured 16 feet wide by 36 feet long, with an 8-foot radius curve. Like the Nissan hut, it used T-shaped steel ribs as the main structural frame. But the American version made crucial innovations. The ribs were formed from two specially shaped sections of steel channel tack welded back to back. This created a serpentine nailing groove that ran the entire length of each rib, shaped like a stretched letter W when viewed from the end. This seemingly minor detail would prove transformative. Instead of drilling holes and bolting the corrugated outer skin and inner lining in place, workers could simply drive nails through the materials into the grooved ribs. The W-shaped bends gripped nails far more securely than wood ever could. The exterior featured corrugated galvanized steel panels curved by the Anderson Sheet Metal Company of Providence, Rhode Island, which developed specialized machinery to bend the sheets to the precise radius required. The interior used masonite pressed wood lining. Between the outer steel and inner lining, paper insulation provided dramatically better thermal protection than the airspace in Nissan huts. The floor consisted of 1-inch tongue and groove plywood supported on a raised metal frame. Pre-assembled plywood sections with doors and windows capped each end. The structure could sit on concrete foundations, on pilings, or directly on the ground. Manufacturing cost ran approximately $800, roughly $12,000 in today's money. But the genuine breakthrough came in the assembly system itself. Fuller delivered Quonset huts in shipping crates. Early versions required 12 crates totaling 3,200 pounds when empty. Within months, improved packing methods reduced this to just 3 crates. A 10-man crew armed with only hand tools, mainly hammers, could erect a complete T-rib Quonset in a single day. No specialized skills needed, no heavy equipment required. Just ordinary soldiers driving nails into grooved steel ribs. In June 1941, the Navy shipped its first Quonset huts overseas under Lend-Lease to Britain. The British, who had invented the Nissan hut 25 years earlier, now received structures that assembled faster and provided superior living conditions. By the end of 1941, approximately 8,200 T-rib Quonsets had rolled off the production line. Early field reports from Iceland demonstrated the design's superiority. Hurricane-force gales ripped the coverings completely off many British Nissan huts and crumpled aircraft on beaches like paper. The Quonset huts emerged practically unscathed. When the Japanese attacked Pearl Harbor on December 7, 1941, everything changed. America's full entry into World War II brought an immediate Navy order for 16,000 Quonset huts. Demand would accelerate as the conflict spread across 2 oceans and 6 continents. Yet even as production ramped up dramatically, engineers began identifying problems with the T-rib design. The curved walls extended all the way to the floor, creating unusable dead space along the sides. Beds, sinks, washing machines, and equipment had to be positioned inward, squandering valuable floor area. Some commanders also requested even faster assembly and lighter shipping weight. Fuller's company developed the Quonset redesign model featuring 4-foot vertical sidewalls supporting a modified arch above. This reclaimed floor space and made the interior substantially more functional. The new arch assembled in 2 sections rather than 3, reducing both erection time and the number of fasteners needed. The modified design used an eye-shaped steel member manufactured by Strand Steel, a subsidiary of Great Lakes Steel Corporation. About 25,000 redesign huts were manufactured at West Davisville, but Strand Steel, already established in the lightweight steel framing market, recognized an opportunity to improve the Quonset even further. The company had displayed its residential steel framing system at the 1933 Chicago World's Fair in an exhibit called Homes of Tomorrow. Now Strand Steel engineers proposed taking over Quonset production and applying their own revolutionary manufacturing system. In late September 1941, the Navy awarded Strand Steel a production contract. Design approval followed in October. Over the course of that 12-month period, Strand Steel took charge of manufacturing operations. By 1943, when production at the Quonset Point facility wound down, Strand Steel had emerged as the leading maker. Otto Brandenberger continued guiding the project through every phase of this transformation. Yet the entire structure underwent radical redesign. The Strand Steel model returned to a complete arch formation, giving up some usable floor space, but gaining extraordinary efficiency in both manufacturing and transport. The breakthrough came in how they engineered the steel ribs themselves. Strand Steel eliminated the T-rib design entirely. Instead, they fabricated ribs from 2 steel channels positioned back-to-back and welded together to form an eye-shaped cross-section. Running between the channels was a serpentine groove that outperformed even the original T-rib concept. This groove permitted workers to use friction-held nails rather than bolts during the entire assembly process. The resulting ribs weighed 35% less than their T-rib predecessors and cost 60% less to manufacture. Beyond that, they required only 2 fabrication stages instead of 3, with straightforward splice connections. This meant fewer individual components requiring tracking, shipping, and field assembly. The Strand Steel model spanned 20 feet wide and extended 48 feet long. Despite being considerably larger than the original 16 by 36-foot model, it weighed substantially less and demanded far less cargo space for transport. The floor transitioned from 1-inch boards to half-inch plywood. The covering switched from heavier gauge galvanized steel to lighter weight material. Panel arrangement was reconfigured so factory curved sections were reserved for the ridgeline only. Remaining surfaces used horizontally laid panels designed to pack flat for shipping, dramatically cutting down transportation volume. A complete Strand Steel unit occupied merely 270 to 325 cubic feet of storage space, compared to 450 cubic feet for the earlier redesign. This consumed less cargo volume than canvas tent systems with wooden frameworks required. The assembly process was elegantly straightforward. Begin by laying out the floor framework and fastening plywood flooring into place. Position each steel rib section and bolt them securely together. Raise the rib sections upright and fasten them to the floor at 6-foot intervals with bolts. Install nailing strips running between the ribs. Attach corrugated steel panels to the ribs and strips, proceeding from the ridge downward along each side. Secure interior masonite paneling by nailing it directly to the ribs, then position the pre-assembled end walls, fit doors and windows, and install interior partitions as needed. Integrate ventilation and heating apparatus where applicable. 10 soldiers equipped with hammers, wrenches, and standard hand tools could complete the entire assembly in a single 8-hour day. No cranes, no welding equipment, no specialized expertise, just personnel following printed directions and driving nails into grooved steel. The strand steel production approach transformed hut manufacturing into a true industrial operation. The Great Lakes Steel Corporation facilities around Detroit ran multiple production lines simultaneously. Steel rolled in by rail and moved through progressive stamping dies that shaped it into channels. The channels were cut to precise lengths, paired together, and tack-welded to establish the grooved rib structure. Each rib section received its splice plates and bolt holes in exact locations. Corrugated panels were sheared to dimensions, with some bent into the required curve for the ridge section. Plywood arrived cut for flooring and end walls. Doors and windows came prefabricated. Every single piece was engineered for perfect compatibility and uncomplicated assembly. Now consider British Nissen hut production by comparison. The Nissen demanded skilled workers capable of managing numerous bolted connections between ribs and supporting members. Each corrugated sheet required careful positioning and fastening with hook bolts. The bracing wires demanded precise tensioning to prevent the structure from spreading. Weather created obstacles to assembly. Wet steel surfaces became treacherous to work on. Freezing temperatures made hands stiff and clumsy. The entire construction process depended on crew expertise and atmospheric circumstances. The Quonset hut concept presented an altogether different approach. Nails worked in any weather condition. The grooved ribs positioned panels automatically with perfect alignment. The eye-shaped steel members possessed inherent rigidity exceeding T-sections, eliminating requirements for additional bracing. An untrained crew might require 12 hours instead of 8, yet they would still produce a functional hut. The underlying philosophy differed fundamentally. British engineers perfected the design first, then trained workers to execute it correctly. American engineers simplified designs so thoroughly that inexperienced workers could scarcely make mistakes. The British designed for skilled craftspeople. Americans designed for rapid scaling with unskilled labor. By 1943, the American approach demonstrated measurable advantages. Building a Nissen with 6 experienced workers under perfect circumstances took 4 hours. Assembling a Quonset demanded 10 workers and 8 hours with no prior experience required. The duration appears longer on paper, yet consider actual conditions. In practice, trained Nissen crews maintained that 4-hour standard only roughly 60% of the time. Adverse weather, exhaustion, or challenging terrain routinely extended construction to 8 hours or considerably longer. Quonset crews facing identical situations might need 10 hours initially, 9 hours on the next attempt, and 8 hours consistently afterward. The Quonset's user-friendly design produced consistency, predictability, and ultimately swifter deployment when multiplied across many teams. Critically, Quonsets required less experienced supervision. A sergeant with basic reading skills could oversee Quonset construction using published instructions. Nissen construction demanded at least one individual who grasped structural theory and proper wire tensioning. When millions entered military service in rapid succession, this distinction held enormous significance. The production numbers revealed the genuine story. Throughout World War II, Britain constructed roughly 100,000 additional Nissen huts beyond earlier production. The United States produced between 150,000 and 170,000 Quonset huts throughout 1941 to 1945, with the upper figure encompassing all variants, including specialized warehouses. American output surpassed British production, despite arriving 2.5 decades later, and accomplished this while simultaneously constructing Liberty ships, tanks, fighters, and all remaining instruments of warfare. Quonset huts traveled wherever American servicemen deployed. They functioned as barracks in Iceland and the Aleutian Islands, surviving temperatures plummeting far below zero. They served as medical facilities across North Africa and Italy. They provided workspace and storage facilities throughout England ahead of the Normandy invasion. They housed troops on Pacific islands spanning from Hawaii to Okinawa. Naval authorities approved Quonset huts for 86 documented applications, including sleeping quarters, religious structures, isolation sections, sanitation facilities, bread production, medical treatment, dental clinics, dining facilities, storage and maintenance areas. The most enormous Quonset hut ever constructed covered 54,000 square feet as a warehouse on Guam, formerly designated as a compound structure. This extraordinary building incorporated rectilinear steel frames combined with arched roof components expandable in both directions, representing a development of the fundamental Quonset concept. The standard 40 by 100-foot version earned the colloquial name Elephant Hut. These enormous buildings provided unobstructed interior space for servicing aircraft and storing supplies. The more typical 20 by 48-foot model, designated as the Quonset 20, became the most prevalent variation. The Pacific Campaign illustrated Quonset's strengths most vividly. Island-hopping tactics required establishing operations on coral atolls, lacking any existing facilities. Everything required maritime delivery. Construction teams battled tropical climate, torrential downpours, hurricane-force storms, and frequently hostile gunfire. Rapid building mattered, simplicity mattered, structural reliability mattered. Navy construction battalions, the celebrated CBs, became masters of accelerated Quonset construction. An efficiently coordinated CB crew could unload Quonset crates, move them to position, establish foundations, and erect numerous buildings within a 24-hour period. The structures emerging from jungle and coral represented the embodiment of American industrial strength, projected across thousands of miles of Pacific waters. The CBs perfected specialized methods for island-based construction. On islands containing solid coral formations, they poured concrete directly on leveled coral surfaces. When terrain proved unsuitable, they drove wooden supports or constructed steel frameworks to raise structures above flood zones. For typhoon-vulnerable locations, they reinforced huts with additional steel cables anchored securely into coral or stone. CB teams accomplished construction at breathtaking speed. On Tinian in the Mariana Islands, builders established a complete air operations center featuring numerous Quonset huts in mere weeks. This location would become home to B-29 operations targeting Japan, including the bombers that carried atomic weapons to Hiroshima and Nagasaki. Every maintenance facility, every storage depot, every command center supporting those missions originated as Quonset containers unloaded from transport vessels. At Guadalcanal, construction battalions assembled Quonset complexes, while enemy forces retained portions of the island. Workers proceeded amid intermittent cannon fire and repeated evening airstrikes. The capacity to establish serviceable structures swiftly, even amid combat conditions, delivered operational advantages the adversary simply could not replicate. Whilst Japanese soldiers occupied primitive shelters or hasty fortifications, American personnel functioned from properly equipped facilities featuring modern electrical systems, hygiene infrastructure, and environmental protection. The Allies continued employing Nissen huts throughout the conflict, especially in North Africa and Europe. The Nissen remained a perfectly workable structure. 4 hours with 6 people represented satisfactory performance, yet satisfactory performance had become insufficient when entire air installations required construction within weeks, and complete military units needed housing immediately after arrival. This distinction emerged most dramatically across North Africa. British forces in Egyptian and Libyan operations utilized Nissen huts, complemented by canvas shelters. Skilled Royal Engineers teams performed the construction. American forces arriving in the latter months of 1942 brought Quonset huts that ordinary infantrymen could assemble, British commanders watched with fascination as American bases took shape with astonishing rapidity. German command observed American construction capabilities with deepening concern. German armaments production emphasized weapons and military vehicles, with housing construction receiving minimal resources. German forces inhabited requisitioned structures, temporary canvas accommodations, or emergency fortifications. The sight of American installations containing hundreds of coordinated metal structures, powered lighting systems, warm water facilities, and methodical organization suggested virtually inexhaustible productive power. German intelligence gathered reports through 1943 onward, documenting American building activity with escalating worry. Luftwaffe photographic reconnaissance documented Quonset settlements materializing on Pacific territories, across North Africa, throughout England. German strategists calculated building speeds and projected overall manufacturing capacity. The numbers seemed impossible. How could any single country manufacture such immense quantities of prefabricated architecture while simultaneously producing warbirds, naval vessels, and armored vehicles in staggering numbers? The response resided in American manufacturing coordination. Strand Steel operated inside Great Lakes Steel Corporation, itself constituting one segment within an interconnected manufacturing ecosystem. Manufacturing techniques producing Quonset huts supplied identical systems for cargo ships, fighter planes, and tank armor. Consistency, standardized components, mechanized assembly procedures, uniformity across manufacturing. These standards shaped every facet of American war production. These temporary military structures became the blueprint for post-war American ingenuity, but their story didn't end when the fighting stopped. When 1945 arrived and the war came to a close, nobody quite knew what would become of all those utilitarian steel buildings scattered across military bases worldwide. Would they simply sit abandoned, rusting monuments to wartime necessity? The answer emerged almost immediately, driven by desperation and need. Across the nation, a housing crisis was unfolding. The government looked at the numbers and saw a staggering shortfall. 3.5 million homes were needed just in 1946 alone. Millions of servicemen were pouring back home, their families ready to start fresh lives. Wartime restrictions had frozen civilian construction for years. The combination created an unprecedented emergency. The War Assets Administration saw an opportunity. They organized the systematic sale of surplus military buildings to returning veterans. At Port Hueneme, California, 801 of these structures were made available to those who'd served their country. When sales began on that first day, the response was overwhelming. Within hours, 600 veterans had claimed 75% of the available units. Across the country, similar scenes unfolded. The structures changed hands for prices ranging anywhere from $295 to $1,000, depending on their size and condition. For veterans, the economics were compelling. A complete building cost substantially less than buying materials alone for traditional construction. But there was a catch: logistics. Each structure weighed roughly 6 tons once broken down for transport. Railroad companies charged 32 cents per £100 to ship them, though groups of 6 veterans could negotiate better rates, bringing costs down to 10.5 cents per £100. Many decided to hire trucks instead, creating an astonishing sight along American highways as these curved metal structures rumbled toward their destinations. Once they arrived at their final location, putting them together proved refreshingly straightforward. The same engineering that had allowed soldiers to erect these buildings on distant battlefields worked just as well for civilians back home. A veteran and a handful of friends could have one standing by Sunday afternoon. The finished product offered more living space than most apartments, yet cost far less than a conventional house. Universities recognized the solution to their own crisis: housing married students. Iowa built an entire community of curved steel dormitories. At Yale, married couples lived in these structures well into the 1960s. In Los Angeles, an ambitious development called Roger Young Village transformed a large parcel near Griffith Park into a thriving community for returning soldiers and their families. Named after a Medal of Honor recipient who died in the Solomon Islands, the village eventually housed around 1,500 families in 750 individual structures. Life there felt surprisingly normal. Neighbors organized community groups, kids played on playgrounds, sports leagues formed, social dances brought people together, schools operated right on the property. Yet everyone understood this was temporary shelter. As veterans found better jobs and accumulated savings, they moved on to permanent homes built the traditional way. By the mid-1950s, the village had largely emptied out. The structures found new purposes. Farmers discovered they made excellent barns and storage buildings for equipment and livestock. Small business owners converted them into workshops and warehouses. One remarkable example emerged in Nashville, where two brothers named Owen and Harold Bradley installed a surplus structure as a recording studio in 1954. Located at 800 16th Avenue South, the studio became simply known as the Quonset Hut. Those curved steel walls produced remarkable acoustics. Patsy Cline recorded Walking After Midnight there in 1957, then later her hits I Fall to Pieces and Crazy. Conway Twitty recorded his breakthrough hit It's Only Make Believe in that same building in 1958. Loretta Lynn would eventually record 5 complete albums there, starting with her first studio record in 1963. Johnny Cash cut his second album in that space in 1958 and would return years later to record Ring of Fire in 1963 and Jackson with June Carter in 1967. Owen Bradley himself eventually became a producer and vice president at Decca Records' Nashville operation beginning in 1958. When Columbia Records purchased the facility in 1962, it became Columbia Studio B and continued operating successfully. But as family housing, these buildings were increasingly abandoned. Veterans discovered that the curved walls triggered uncomfortable memories of military barracks. The interior was cramped too, only 960 square feet of usable space, and the sloping sides made much of that impractical. Growing families needed something better. By the early 1950s, most communities built from these structures were being replaced by conventional housing developments. Still, the structures persisted elsewhere. Thousands remained on military bases worldwide. Countless others found homes on farms, where their clear interior spans and weatherproof steel construction proved ideal for storing crops and equipment. 7 decades after World War II ended, these buildings remain visible across the American landscape, testaments to remarkably robust wartime engineering. The British Nissan huts followed a different path entirely. After the war, many were adapted for farming and industrial purposes. Thousands provided housing for post-war migrants throughout Britain, Australia, New Zealand, and other Commonwealth nations. In Belmont North, New South Wales, 50 of these structures were built as private homes. 17 have been torn down over the years, but 33 remain occupied and have been carefully restored. In Britain, surviving Nissan huts dot former military sites, now serving as workshops, storage spaces, or preserved as historical artifacts. One stands in the Chiltern Open Air Museum with an authentic RAF briefing room inside. Some have been converted to businesses, proving the enduring practicality of wartime designs. The contrast between these two approaches reveals something profound about American versus British engineering philosophy. The British emphasized elegant design and efficient manufacturing processes. The Nissan hut used relatively few components, straightforward T-shaped ribs and corrugated panels that were simple to produce. Designers assumed trained crews would handle assembly competently. American engineers pursued a different strategy. They prioritized simplicity for the person actually building it in the field. Curved steel sections added manufacturing complexity and required grooved ribs that were harder to produce than simple T-sections. But this manufacturing burden transformed assembly from skilled work into unskilled labor. The grooved ribs essentially guided the worker, turning construction from a craft into something anyone could accomplish. This philosophy extended throughout American wartime production. The M1 Garand was more complicated to manufacture than the British Lee Enfield, yet any draftee could maintain it. American tanks used straightforward transmissions any mechanic could repair, while German tanks featured sophisticated drivetrains that demanded specialist knowledge. Liberty cargo ships were built using standardized parts and assembly line techniques that achieved 3 ships per day at peak production. Speed of deployment mattered more than design elegance. Training ordinary workers took priority over achieving perfection. Producing massive quantities meant more than perfecting individual units. These principles, debated fiercely at the time, ultimately proved decisive. Between 150,000 and 170,000 Quonset huts emerged over 4 years of wartime production. Taking 160,000 as the midpoint, that represents approximately 308 huts weekly, 44 daily, nearly 2 every single hour around the clock for 4 consecutive years. Individual craftspeople couldn't match this output. Traditional building methods couldn't approach this scale. Modern prefabrication owes an enormous debt to this innovation. The fundamental principle, moving complexity from the field into the factory, underlies everything from modular homes to contemporary steel arch buildings today. The grooved rib concept reverberates through modern construction. Steel studs for residential framing use channels that grip drywall screws through friction alone. Prefabricated wall panels employ proprietary connection systems, eliminating the need for traditional framing knowledge. The principle stays constant. Make components intelligent so workers don't need to be. Global manufacturers now produce Quonset-style buildings using contemporary materials and methods. Modern versions employ galvanized steel with advanced corrosion-resistant coatings and can withstand Category 4 hurricane winds and extreme snow loads. The fundamental concept remains unchanged. Semicircular profiles provide inherent structural strength. Components prefabricate for efficient shipping. Assembly requires only basic hand tools. Alaska contains thousands of original World War II-era Quonsets, making the design so prevalent that some areas restrict new construction to prevent further proliferation. These military structures, built with urgent wartime necessity 70 years ago, continue functioning as homes, businesses, and storage buildings, proof of extraordinarily robust wartime construction standards. Ultimately, the Quonset story is about industrial philosophy. Britain designed something good and trusted trained users to execute properly. America designed something so simple that untrained users couldn't execute improperly. Both approaches had merit. But when total war demanded rapid mobilization of millions of civilians into military service, the American approach proved superior. The difference between erecting a building in 4 hours versus 8 hours seems minor. Multiply that across thousands of bases on 6 continents over 4 years of warfare. The Quonset's assembly speed represented thousands of saved man-hours, thousands of soldiers freed for other assignments, thousands of structures erected by crews who would have struggled with more complex designs. Construction speed alone didn't win World War II, but the capacity to project industrial capability anywhere on Earth, to establish functioning bases on remote islands within weeks, to house and supply millions of personnel across dozens of countries simultaneously. These capabilities profoundly shaped the war's outcome. The Quonset hut was one element of a massive industrial apparatus, but it embodied the principles that made that machinery unstoppable. 10 workers with hammers could complete one in a single day. That straightforward fact represented a military construction revolution, a monument to American manufacturing thinking, and a contribution to victory that historians frequently overlook. The British Nissan hut performed admirably for 3 decades. 6 men building one in 4 hours represented impressive achievement for 1916 technology. By 1941, circumstances had transformed utterly. Total war demanded solutions operating at industrial scale. The Quonset delivered through a seemingly simple innovation. Construct it so straightforwardly that anyone could do it. Today, curved metal buildings housing farm equipment or serving small businesses represent descendants of that World War II creation. The Quonset proved revolutionary advancement doesn't require exotic materials or complicated technologies. Sometimes innovation arrives by asking different questions. Not how do we build this better, but rather how do we build it so simply that anyone can build it at all. That became America's true advantage in the global conflict. Not merely the capacity to produce more tanks, planes, and ships than competitors, but rather an engineering philosophy that every product, system, and structure should be designed for mass production by ordinary workers and field deployment by ordinary soldiers. The Quonset, erected in one day by 10 men wielding hammers, embodied that thinking perfectly. It wasn't the most elegant answer, it was the most effective answer at the scale that counted. The British Nissan Hut was good. The American Quonset was good enough, faster, simpler, and in 1941, that distinction meant everything.